Thank you, and good afternoon, everyone. So I'm going to say a bit about the side effects of high magnetic fields over the next 29 minutes and 56 seconds. So I should say I have no declaration of, I have no financial interests or relationships to declare. So MRI over, I guess its history has shown a sort of inexorable rise in the operating fields. This just shows the variation of the composition of the install base of MR systems between 2001 and 2012, showing the significant increase in the proportion of 3 Tesla systems and the reduction of low field systems in that period of time. Over that period, though, there have also been a very significant increase in the number of systems operating at, I guess, high field or ultra high field, so above 4.7 Tesla. So now there are something like 7 Tesla systems in operation. At least 4 9.4 Tesla systems have been developed and operated for some time. And as you're probably aware, there's a 10.5 Tesla system in Minnesota, and there are 2 11.7 Tesla systems under development as well. And in Nottingham, my own institution, we've sort of followed that path of increasing field over the years. And of course, the reasons we do that are we get a very significant increase in the signal-to-noise ratio, increases in contrast, which can be exploited to produce the rich, beautiful images that we all enjoy. And that carries on as you go up to even higher field, up to 7 Tesla. But of course, there are some associated side effects of operating at high field, and most of those effects are associated with the elevation of the static field itself. But there are also some knock-on effects in terms of gradients, the effects of gradients, and the effects of the RF on the subject. And of course, there are additional implications for uses of implants, which I won't really touch on, but I think will probably be picked up later in the session. So as a result of these potential side effects, there are of course regulatory limits on use of different field strengths set by various different bodies. So for example, ICNIRP, the International Commission on Non-Ionizing Radiation, have set these 3 different modes of operation. So normal operating mode below 4 Tesla, controlled operating mode between 4 and 8 Tesla, and above 8 Tesla, an experimental operating mode. The FDA, in terms of adults or adults, children and infants, put a divide at 8 Tesla. For neonates, the divide is at 4 Tesla. And then the IEC, the International Electrotechnical Commission, who sort of focus more on the MR systems themselves, divide things up into these different operating modes with boundaries at 2 Tesla and 4 Tesla. So those of us working at 7 Tesla are working in this second level controlled operating mode where IRB approval is required. And basically, these operating modes above the normal level required increased levels of medical oversight, subject monitoring, and ethical approval. And of course, there are also interactions with those working around systems at high field, and so there are various occupational standards that have been set by different bodies. Just focusing on the ICNIRP set levels, they suggest a whole body maximum exposure of for occupational purposes of 2 Tesla and a whole body average exposure over 8 hours of 200 millitesla. So you've heard already in the earlier part of the session, the main effects relate to the effect of the static fields, which can take a variety of different forms, often not just this pure static field, but also related to the effect of changing fields, but at very low frequency as people move within the field, or parts of their body or their blood, for example, move within the field, you get effects. Then you have the effects of the applied gradient fields, which are typically going on at tens of kilohertz, and then of course the effects of the RF, which is applied at tens to hundreds of megahertz. So let's look at these effects and their relationship to operation at high field sort of in turn, but starting at the sort of the RF level, going to gradients, and then to the main topic of the talk, which is the static field effect. So, of course, you've heard already about the interaction of RF with the human body, which we relate to the power that is deposited in tissue. This sort of the power per unit weight is usually the limit that is used, and so, for example, we could focus on a whole body limit of 2 watts per kilogram. So the issue in going to high magnetic field is that the specific absorption rate, this deposition of energy in the tissue, scales with the square of the static magnetic field in a uniform B1 field at the same B1 field level, and that's because the energy that's deposited takes the form of a current flow in the tissue, and the induced current depends on the rate of change of the applied RF magnetic field, and that rate of change scales with the frequency. So we end up with a scaling as the square of the field. More importantly, as you go to, or equally importantly, as you go to a higher field, then as the RF frequency increases, the RF wavelength decreases, and you end up with a situation where you get significantly spatially varying fields inside tissue and similar spatial variation of the deposited power. So just to illustrate this, some simulations from a paper from some time ago by David Holt, just looking at the variation of the B1 field in a 10 centimeter spherical object with different conductivities, with the dielectric properties of water, just showing that as you go from 100 megahertz to 200 megahertz to 400 megahertz, you get this spatial variation of the applied B1 field, and that's also manifested in the SAR. And that behavior also manifests in simulations of a human head, again from some time ago, but quite nicely illustrative, just showing on the, let's take this one, this is a quadrature mode RF applied to the human head. On the left side, you see the variation of B1. On the right side, the variation of the SAR, the power deposited. And at 63 megahertz, there's a pretty uniform pattern of both these features. But as you go to the higher frequency, the pattern becomes more heterogeneous. You get these hot spots of SAR, and the B1 is less uniform. So in part to ameliorate that, we're moving to systems where you have not just a single RF transmitter, you might have 8 different RF coils with separate transmitters connected to them, which opens up opportunities for flattening out and making more uniform the SAR distribution and also the B1, but also opens up additional risks because you may get things wrong and actually increase the SAR by getting the wrong superposition of the fields. So just to sum up that part of it, so with increasing V0 field strength, when we're thinking about RF fields, we have the same limitations on SAR, but the power dissipation increases because we're operating at higher frequency, and we get this reduction in homogeneity, which has to be taken account of, and the availability of multi-transmit brings risks as well as some opportunities. So moving on to the gradient fields, as you heard earlier, these can introduce effects in interaction with the human body because the induced currents within the tissue can stimulate peripheral nerves as a result of the changing magnetic field when you switch the gradients on and off or reverse them. But that effect is essentially independent of the applied static magnetic field. So the currents we get by changing the gradient fields, they don't really change as we operate at 7 Tesla or 3 Tesla, and so that's not really something that is impacted on by working at high field. However, the effect that was also touched on earlier of acoustic noise, which we're all well aware of, arising from the gradient coils, that will scale with magnetic field because the acoustic noise arises because of the force on the current in the gradient coil windings. So this is a gradient coil system here. You have current flowing in these wires. The current is a lot of the time perpendicular to the applied field, and as a result it experiences a force. That force is fluctuating at audio frequencies, and the force is directly proportional to the applied field, and so it goes up as you go to operate a high field. And obviously the manufacturers in particular and operators of systems have to worry about this, provide appropriate hearing protection and engineer the system so as to minimize the noise level, to reduce resonances of the system and so forth. And just to show, it's sort of obvious that if you look at systems operating at different field strengths, and this work from the late Bill Edelstein from some time ago, you see that using similar sequences and operating at different field strengths, the sound pressure level generated, it does increase with the field strength. However, there's a caveat on that, in that the manufacturers obviously know that the driving force is increasing, and so typically there's better engineering in the systems in order to reduce the noise production. So actually working at 7 Tesla, it isn't necessarily the case that the acoustic noise is significantly worse than working at 3 Tesla. So for the gradient fields, the propensity for peripheral nerve stimulation doesn't really change, but the force on the gradient windings increases, and that has to be ameliorated by improved engineering to avoid excessive noise levels as you work at ever higher magnetic fields. So moving on to the main piece, increasing the static magnetic field. What kind of effect can that have? Well, there are a variety of interactions that can go on. The first is that if we have any charges moving inside the tissue of the human body, then that charge moving in a magnetic field will experience a force. So the force is just given by the vector product of the velocity and the applied field. And so that obviously scales up with increasing field strength. And that the force will produce flow of charge, produce a current itself, and that will scale as the applied field. But that current itself experiences a force from the effect of the applied strong static magnetic field, and that effect, which is known as a magnetohydrodynamic effect, scales as the square of the magnetic field, so will increase more rapidly with applied field strength. Similarly, if we have any material which becomes magnetized in the applied field, or is magnetized naturally, it will experience a force in the field. We can work out what that force is by thinking about the energy of a little piece of magnetization in an applied field. And if we're thinking about interaction with the human body, so we're working with essentially the susceptibility of tissue, which is normally very close to the susceptibility of water, about 9 parts per million, so very small and actually slightly negative because the water is diamagnetic. So under that situation, we can work out that the force experience depends on the gradient of the square of the magnetic field, and also depends on the susceptibility of the material. So that's a vector, but if let's just look at the force in one direction, then it will depend on the product of the field in that direction and the gradient of that field in the same direction. So the force depends on the product of the field and gradient, which both you might expect to scale up as the magnetic field strength increases. And because it's proportional to the susceptibility of this force, it will be a negative force for watery diamagnetic materials. And if we have anything paramagnetic or we hopefully very much avoid having anything ferromagnetic, which experiences a positive attractive force. So if we take a 4 Tesla system, which is described nicely in this paper by John Schenk, then if you look at the magnetic field, obviously that's very uniform in the middle of the magnet, and then it drops off. So correspondingly, the gradient of the magnetic field is sort of 0 in the middle of the magnet, and then increases as we get to this region of rapid field change, and then drops off more slowly. So the product of the field and the gradient on axis in this case has a quite strong peak here, and on this system takes a value of about 8 Tesla squared per meter on this system. So anything watery that's placed here is going to experience a repulsive force which tries to push it out of the magnet as opposed to being pulled into the magnet. taking that to the extreme, if you specifically design a system, you can make a gradient field product of greater than 1300 Tesla squared per meter, and that's enough to balance the force of gravity, and then you can levitate watery objects of your desire. In this case, just a water droplet, which is being levitated. In a 7 Tesla passively shielded system of the kind that we have in Nottingham, many people, the first wave of 7T systems use this magnet. Then, if you look inside the magnet, you find, if you look at the force sort of on axis, the BZ, dBZ by dZ term, that reaches a value of about 46 Tesla squared per meter, which is going to produce a force which is about 3% of gravity on a watery object. Inside an actively shielded system, it's maybe more like 59 Tesla squared per meter. So what are the possible effects that these interactions can give rise to? So there are a list of these which we'll come to touch on, well, most of them, maybe not that one, but so let's put this in the context of some recent work which is looking at the subjective perception of being scanned at 7 Tesla. This is the first paper from the Essen group, where people were asked to, sort of 100 subjects were asked to report the sensations that they sort of noticed during a variety of 7 Tesla scans. And you see that quite a strong, the strongest sensation is vertigo, noted by about a quarter of the people, then nausea and metallic taste, things that we'll touch on. Light flashes, also noted by some. But in this group, a proportion of whom were also scanned at 1.5 Tesla and reported on their perception of the scanning, and were asked to report on the causes of discomfort. Despite this effect, the majority reported exam duration as the largest cause of discomfort at 7 Tesla and the acoustic noise at 1.5 Tesla. There have been some other more recent similar studies. This is by the Leiden group, 101 subjects. And just without going into too much, the yellow or red means that some sort of effect was felt. And you see again that dizziness on moving into the system features pretty prominently in this. This is a more recent paper from the Berlin group, 165 subjects who underwent a cardiac exam. And again, dizziness is featuring pretty strongly up here, although it's only something like 13% of subjects who are reporting experience of dizziness in this case. And there's some other papers which are in the references of the in the syllabus. So let's look at some of these effects in terms, and let's take on the main one first, which is dizziness or vertigo, which is the thing that's reported by most people. So this is something that I guess people have thought about for some time, but it's only really relatively recently become understood. We've known, I think, for some time that it's an interaction directly with the vestibular system. So vestibular system made up of the semicircular canals, 3 of them in each inner ear, which sense the acceleration through rotation in different axes, and then also the utricle and saccule, which sense acceleration in a vertical or horizontal sense. So there's a variety of possible candidate mechanisms that have been put forward. These include, or the 3 I'm going to look at, are the force on the continually flowing current inside the part of the semicircular canal, the effect of the small differences in susceptibility of different parts of the vestibular system, and the effect directly of currents induced in the vestibular system by moving in the magnetic field. So taking first the susceptibility effect, well, it turns out that within these accelerometer systems, in the utricle and saccule, there's this gelatinous membrane which contains these sort of lumps, essentially, of calcium carbonate, which sort of add to the weight of this. This moves relative to these hair cells during acceleration, and that's what gives rise to the sense of acceleration. But these calcite materials also have a different magnetic susceptibility from the surrounding material. So if they're placed in this region of strong field gradient product, they'll experience a force. And making some estimates for the density and susceptibility of the calcite material relative to the surrounding stuff, you can estimate about 1% of G might be the effect. And I think it's known that 0.1% of G can be sensed. So it's a potential candidate mechanism, but it's one you'd only expect to be felt. It will be felt in a region where there is a significant field and a significant field gradient at the end of the magnet. We also have the direct effect of current induced in the vestibular system by moving in the field. The vestibular system, as we heard, has, as I sort of said, has a continuously flowing current here, and also it has continuous firing, which is just modulated by, in the case of these hair cells which sense the potential movement, it's modulated by their bending to increase or decrease the firing rate. If you apply an additional current as a result of movement in the field, that will also modulate the firing rate and give rise to a sensation of movement. So again, a potential candidate, but it requires candidate mechanism. It requires a change of magnetic field to be occurring for that to be perceived. Well, actually, the one that turns out to be the most likely candidate is the direct Lorentz force on this continuously flowing ionic current within particularly the semicircular canal. So this is some really great work by a group in Baltimore from 2011 who really explored this effect in great detail. So here are the two of the semicircular canals, they're sort of in the horizontal plane, the fields running in this direction in yellow, and there's this continuously flowing current just focusing on this JA, and that's perpendicular to the field, and so there's going to be a force on that current, and that force is going to be such that it will deflect the membrane which senses the movement of the fluid within the semicircular canal. So it's going to give a perception of rotation in this direction as a result of that force. If you put in some numbers, then you find that you could expect to get about 23 millipascals for some very simple estimates, but it's known that nystagmus being this production of movement of the eye through the vestibular ocular reflex, can be generated with much lower pressures than this. So we could expect to find this effect, this nystagmus, occurring during exposure to field if this sort of effect was occurring. And in fact, that's exactly what the Roberts group found. They exposed a number of subjects in complete darkness to 7 Tesla field. So this is showing a component of the nystagmus, which is essentially, this is a little insert, a little section of time where you see this period of slowly constant moving of the eye, and then this sudden flick back, which you hopefully saw in the previous animation. So that rate of change is plotted here. And you see that for an exposure of up to more than 20 minutes, this nystagmus persists. And so this seems like something that couldn't be produced by forces on the effect of induced currents because the person is in a static field and not moving. It can't be due to the susceptibility effect because they're in a uniform field. So this seems like the right mechanism. It also has the effect that the direction of the nystagmus reverses when you put someone in at the wrong end of the magnet, so you reverse the direction of the field with respect to the current flow. And also, if you move someone, well, in this case, in a 7 Tesla system or into a 3 Tesla system where actually the rate of change of magnetic field on entry into the system is greater in the 3 Tesla system, the nystagmus is less than in the case of the 7 Tesla system. It follows the static field, not the rate of change of field. So this looks like the candidate system. My colleague Paul Glover in Nottingham sort of looked at this in some detail, and he found that the detection of nystagmus occurred at a static field of about 1.5 Tesla, and that was linked to the subject's perception of unnatural movement on movement into the scanner, and that occurred with a mean threshold of about 5 Tesla, although there's a significant variation across subjects, and it was found that this, the onset of nystagmus was correlated with the onset of perception as well, although they occurred at particularly different field strengths. And Paul was also able to show that you could model this quite nicely with a fairly simple model where you have a sort of low-pass filtering. It takes a certain amount of time for the effect to be perceived, and then there's a slower negative adaptation, which means that if you look at the response, you end up with this initial peak and then a slow decrease. But when you move someone out of the magnet, if you take them away from the field, then you get a reversal and a sort of significant effect. So people report the effect of vertigo after being moved out of the magnet after a long time in, as well as being in, but as well as whilst they're going in or inside the magnet. And it's because of this adaptation that's going on. And the Roberts group were also able to show that if by changing the angulation of the head in certain subjects, you could eliminate the perception that the nystagmus, by angling the head forward, although it was variable across subjects, probably because of the variability of the anatomy of the semicircular canals. So this main effect, we can say, is most probably generated by this Lorentz force. But there's a lot going on. We're talking about a complex interaction of time constant magnetic field history, which means it has been something that's quite difficult to probe and understand. There's sort of cognitive effects going on as well. Just to pick up a couple of the other effects that people highlight. So there's this perception of metallic taste on usually moving into or moving around a magnet is felt by many subjects. And that's resulting from essentially induced currents around the surface of the tongue. We find that typical rates of change, a field of 2.3 Teslas per second, were required to generate this taste. And essentially it's the same effect that can be used to stimulate the taste buds by electrical current. It's the taste you get if you are inclined to put a battery across your tongue, you'll get this sort of slight metallic taste. You can avoid it going into the magnet by sticking your tongue out, but probably explain what you're doing before trying that. The other effect that some people report is magnetophosphine, so light flashes perceived usually with quite rapid motion of the head inside the field, sort of flash of light. It's very sensitive to the light level that's around at the time. It's most likely a result of the induced current in the retinal surface. Again, it's a relatively low level of current that's induced, much lower than the sort of currents you need to get peripheral nerve stimulation. But you can induce it quite easily with a solenoid, and you apply a changing magnetic field. So then effects on cardiac function, something that haven't been perceived, but something we perhaps should worry about. So there is going to be a force on the conductive blood flowing in the magnetic field. If you think about the aortic arch, that's where the flow is perpendicular to the applied field. That force produces a charge separation, a current flow, and that induces voltages at the surface of the body, which we're all very well aware of. That's the modification of the T wave, depending on the strength of the imposed magnetic field. So getting worse here, 1.5 Tesla, 3 Tesla to 7 Tesla. So the worry is that if you go up to large enough field, the kind of voltages that were induced could be enough to actually re-stimulate the sinoatrial node, but sort of simplistic calculations estimate pretty large fields required to do that. But perhaps more close to where we are, this magnetohydrodynamic effect produces a back action on the velocity, and that's estimated that at 10 Tesla that could produce a pressure change about 5%. It scales as the square of the field, so it could go up to 10% at 15 Tesla. So that might be something that kicks in if we go to even higher magnetic fields. There have been quite a lot of studies already of the effects on vital signs of exposure to 7 Tesla, 9.4 Tesla, but no significant changes have been found as yet. Variety of cognitive effects have been reported, not very much in these particular studies. And I don't know the literature in great detail, but if you look, there is quite a lot of variation across the literature. This is a nice meta-analysis which I think reports for some cognitive effects an effect size on average of about 0.14. So it's pretty small effects. It's a complicated literature, needs further investigation. So just summing up on this then, so these dizziness of vertigo effects, they're important. They vary across individuals. We do need to consider these side effects in planning work practices. We think we understand what's going on, and we probably need to worry about effects on cardiac function as fields go up even further. So thank you very much for your attention.